So we just learned how to balance these redox equations. So now we want to take this further and figure out how do we use that redox reaction to connect that with electricity to produce electricity. And so the type of system that we use to study these is what we call electrochemical cells. And there's two types of them. There's a type that we call voltaic cell or galvanic cell. And this is a type of system that's set up to harness or to get the energy from the spontaneous chemical reactions, from those redox reactions, and then convert them to electricity. And so anytime you use a battery, they're all examples of galvanic or voltaic cells. Now, there is the other type of cell called the electrolytic cell, and this is type of electrochemical cell where you have a non-spontaneous chemical reaction, which means its delta G is positive, and you're trying to make it happen by running electricity through it. The setup that you do there uses the same principle that you're going to learn in electrochemistry, so that's why both of these cells are grouped as belonging in the electrochemical cell. Okay, so this picture just shows you what the two looks like. In a galvanic cell, you basically have a reaction happening, and I'll talk in more detail on how this works, but as a result of the reaction, electron is being transferred from one compartment to the other. As the electron moves, it generates kinetic energy. That kinetic energy is then used to do some work, in this case to light this light bulb. In the electrolytic cell, it's the opposite. You have a power source, which of course has its own electron flow from an outside source. And in this case, you're using that electrons to make this flow of electron from one compartment to the other that is initially non-spontaneous. You're trying to make that happen. So you're basically attracting the electron to go this way and then to go the other way by using this outside energy source. And that's what we refer to as an electrolytic cell. So what we're going to spend most of our time talking about in this chapter is the voltaic cell. And so we're going to start by just discussing how we design a voltaic cell conceptually that would make it able to use that chemical energy to generate electricity. So we know for a long time that there's spontaneous reactions that happen when we put, a piece of metal in a solution of ions from other metals. So for example, here, if I take a zinc metal and I put it in a solution of copper sulfate, the solution is blue there because there are copper ions that are floating around. As you leave that arrangement for a long time, you see that solution becomes less blue now on the right side. And that's because much of those copper ions that are floating around is now becoming copper solid, which is actually deposited on the surface of that zinc metal. On the other hand, the zinc metal itself has disintegrated somewhat, and so it's no longer as long as it was originally when it started. So a good chunk of that zinc metal actually has become zinc ion, which is soluble in the solution. And so we know this reaction happens spontaneously. You don't need to provide any energy for this to happen. The question is, how do we then get the energy that is actually generated by this spontaneous reaction to do work for us? Okay, this would be the actual reaction that's happening. So again, the copper ion becomes copper solid. In this case, accepting 2 electrons, the zinc becomes zinc ion, releasing 2 electrons. So that's the oxidation, and the copper reaction is the reduction. So when we combine them, we get our redox reaction. And we're trying to figure out how we use that electron to actually do some work. Now, if we just put it in a beaker the way that I just showed you in that picture earlier, nothing's really going to happen because the electron is going to move from the zinc to the copper, but all it's going to do is generate heat. That movement is not going to be used to do anything useful. So in order to make the electron actually do something useful, we have to separate the two reactants from each other and make the electron go through a specific path, right? And that path is what allows the electron to do some work. So the picture now looks something more like this. We put the zinc in one side, and in that solution, again, we need to provide solution there because the electrons can't really move unless there are ions present. So you have zinc ion in that solution on the left, and then we have another compartment on the right where the copper and the copper ion is available. And then we know that the zinc will spontaneously release electrons to the copper. The copper will spontaneously accept that electron. So by allowing that electron to go through this path, which is our wire, and if we put a light bulb in the middle, then that movement of the electron will actually generate enough kinetic energy to light up that light bulb. Okay, So let's talk about this whole setup here. This is what we call a voltaic cell or a galvanic cell. And so the components of the galvanic cell are as follows. First, you need to have the two compartments, okay? So one compartment on the left, that's the oxidation compartment, right? Because that's where the electrons are leaving the zinc. And on the right side, you have your reduction compartment, which is where the electrons is coming in towards the copper ion. Now, we call those different names. So on the left side, we call it the anode, and on the right side, we call it the cathode. Now, because the left side is where the electron is coming out from, the right side is where the electrons is going to, that must mean that the left side is more negative than the right side, right? Because that's where the electrons, there's more electrons on the left side, that's why they want to go to the right side. So therefore, the anode has a negative sign, and the cathode has a positive side. This is, in fact, if you ever look at a battery, it always has that positive and negative. That refers to the cathode and the anode on the battery, okay? Now, in order for the electrons to flow, you have to have electrolytes on both sides. That's what these solutions are. So you have ions in there, zinc and copper ions. You have to have pieces of metal as well connected to the electrolyte, because the electron is going to be generated, it's going to travel through the metal and then through the wire. So those metals are what we call electrodes. Now, if the metals themselves are actively involved in the redox reaction, like both of these zinc and copper electrodes are, they're actively involved, we call those active electrodes. Okay, active electrodes, because they're actively involved in the reaction. Sometimes, as you'll see later, not all electrodes are always involved in the actual redox reaction. Some electrodes actually are just there to provide a path for the electron to flow. So when that's the case, we call it inactive electrodes, okay, because they're not actually involved in the reaction. They're merely just a way for the electron to be able to go from one place to another. The other thing that is needed here is something called a porous disk, or you will also hear the term salt bridge, okay? And this is something to do with just the way electrons flow and the neutrality of charges. So if I don't have this thing that's colored green in the middle, so that's what the porous disk is. If I remove that completely and just put like I don't know, a piece of wood, for example, in between those two compartments, the electrons does not want to go and flow from left to right here. It will just stop. The light bulb will not turn on. Question is, why is that? Well, the problem is that as soon as some electrons flow out that way, then what's left on this side is just a bunch of the zinc ion, because the electrons are flowing that way, so there's a lot of positive on this side. If the electrons are flowing this way, that means there's a lot of negative on this side, right? And so as soon as there's a lot of buildup of negatives and a lot of buildup of positive on this side, then the electrons have no longer has the incentive to want to leave this compartment, because there's all these positive that are attracting the electron. So it will just sit there and it's not going to move. In order to make this movement continuous, you have to balance out the charges. So in other words, for every positive that's generated, there has to be a negative ion that is able to neutralize that. And for every negative ion here, there has to be a positive ion that's able to neutralize that. The way we do that is we put in between these two compartments a disk that's made up of some kind of ionic compound. Usually potassium nitrate is a common one, or sometimes we just put a piece of wet paper that connects the two compartments, with that paper having been submerged into an ionic solution, so there are ions on the paper itself, and it could basically release some of those ions into the appropriate compartment. So on this side, it will release some of these negative ions. On this side, it will release some of the positive ion, balancing the charges. Once the charges are balanced, then the electrons can flow some more again from the anode to the cathode, okay? So that's the function of what we call a salt bridge or a porous disk, and that's an important component of the electrochemical cell, which in this case is the galvanic cell, okay? So in summary, here's some components of it. Electrons move from left to right through the wire. The left side is the anode, that's where oxidation occurs. And then the right side is the cathode, that's where the reduction occurs. The anions, in this case, are going to move to the left side because there's a lot of positives that's being generated as a result of the electron moving away. So the anions are going to move to the left side to balance out the charges that's coming from the salt bridge. The cations, on the other hand, is going to move to the right side to balance out that electrons that are coming in here. So there's a lot of negative charges here. You're going to need some cations to balance out that charge, okay? All right, as I said earlier, sometimes we can have these electrodes that are not actually involved in the redox reaction itself. It's just providing a path for the electrons to flow. Those are called inactive electrodes. So here's an example. So in this particular redox reaction, the oxidation is from iodide going to iodine. The reduction is permanganate ion going to manganese 2. So you can see that all of these species right here are not metal solid, right? If they're not metal solid, that means they can't conduct electricity. This is an ion, that's a solid, but it's non-metal. Both of these are not solid metal either. And remember, you need solid metal for the electrons to flow, because the electrons can flow here, but in order for it to go from here to here, you need some piece of solid metal. So what we do here a lot of times is we just pick something that is a metal that is not reactive, but it's still a metal that allows electrons to flow. In this particular case, we use graphite, which is just solid carbon, and that conducts electricity. We could also a lot of times use platinum. There'll be another one that you would see, or sometimes gold. And so both of these things, graphite or platinum, are the common inactive electrodes that you would see. Okay, so now I want to summarize the components of a voltaic cell. So every time you have to draw a voltaic cell, you want to include the following components. You want to have all the electrode materials, which is the anode and the cathode, the ions that are in the solution for each compartment, and then any other species that's involved in the reaction. Give the name of the electrode, both the anode and the cathode, so you got to label them. And then make sure that you show the charges. Remember, the anode is the negative side, the cathode the positive end here. And then by convention, we usually draw the anode on the left side. Each half reaction and the overall cell reaction should be provided in the next to the diagram, so that it's clear what kind of reaction we're looking at. Show the direction of electron flow, and then the movement of the ions from the salt bridge that would balance out those charges, okay? There's a lot of things to do there, obviously, right, to create all that diagram and to write the reaction. So sometimes in electrochemistry, there is what we call a shorthand or a line notation that just makes illustrating all of those components of the electrochemical cell a little easier. And so the way we do that is we separate out the two compartments using a double vertical lines. And then on the left side, we write all the anode components. On the right side, we write all the cathode components, okay? And then between the anode side and the cathode side, on its own, we're separating them by a single vertical line. So the single vertical line here basically put in the anode metal that you use for the actual anode. Remember, that's the piece of metal that actually allows the electron to go. And on the cathode side, you also put the cathode metal here, separating it by a vertical line. So this is the anode reaction, this is the cathode reaction, this is the anode metal, and this is the cathode metal. Okay, so just a quick example, that zinc and copper voltaic cell that I showed you earlier, zinc is our anode, copper is our cathode. So if I want to write it for the shorthand notation for that cell, it would look something like this. I put that double vertical line that represents our salt bridge. And then on the left side here is the anode reaction. Well, the anode reaction happens to be a zinc oxidized to zinc 2 plus. However, the zinc sulfate itself also serves as the anode metal. So that's why I put a vertical line here to separate the zinc solid from the zinc 2 plus ion. If both of these things are aqueous, then you would have a vertical line here to represent the actual metal that you use, and then you just write the reaction there. And then on the cathode side, I know that the reaction is copper 2 converting into copper solid, but since the copper solid is also the cathode metal in this case, I put that vertical line to separate out the two. And so now I have a shorthand way of writing this voltaic cell between zinc and copper. Okay, let's now take a look at an example on how to draw that voltaic cell that I just described. And we want to draw the voltaic cell completely, have the equations, and then use the line notation as well, right? So we want to use that shorthand notation as well. So we're going to do everything here just to illustrate what's going on. Now, let's take a look at the information that they gave us. They told us that it's a voltaic cell. It consists of one half cell with a chromium bar in a chromium nitrate solution. So that tells you that the chromium is electrode, right? And then there is chromium nitrate where the electrodes is submerged in. And then the other half cell has silver with a silver nitrate in it. Okay, so then the silver must be the other electrode. We have a KNO3 salt bridge, and then measurement indicates that the chromium electrode is negative relative to the silver electrode. So what that means is that the chromium side is more negative, which of course means that that's the source of the electron, where the electron is going to flow out from. So that means the chromium is the anode and the silver side is the cathode. If I were to draw this, this is what I would start with. I would start with a drawing that looks like that, just to have the two compartments. And then on one side, I'll put in my solutions, and then afterwards I put my electrodes in. Remember that one electrode is going to be chromium, so this is chromium solid. The other one is going to be silver solid. And then I have some chromium floating around here. I have some nitrate floating around. I have some silver floating around. I have some nitrate also floating around. This is my salt bridge, so I usually just label it that way. That's made out of KNO3, and so electrons is going to flow out from the anode, which is the left side. We were told that that's the side that's more negative, right? So it's going to go that way. So the electron flow is going to look like that. And I just put electrons over the top to indicate that that's where the electron is going. And then the last thing is just to indicate the flow of the ions, right? So remember that the left side is where electrons are coming out from. So if it's coming out from the left side, that means it becomes more positive. That means the nitrate is going to flow in from the salt bridge here. So nitrate is going to flow in here. Whereas to the right side, you're going to have the potassium balancing out the flow of the electron, okay? Last thing is just to put the word cathode there to complete that picture. Now, if I want to write the reaction, then I know that the oxidation goes from chromium to chromium 3. How do I know it's chromium 3? Because they gave us that formula in the question. They said it's chromium 3 nitrate. And then so this is plus 3 electrons. And then on the reduction side, I have silver. And reduction means that I'm accepting electron, right? So silver is a plus 1. Again, that's given in the formula, that's given in the question. So this becomes Ag solid. So that would be my reaction. So if I want to balance this, I'll multiply the bottom by 3, the top by 1. That's a pretty easy one to balance. So I get chromium solid plus 3 Ag plus goes to chromium 3 plus 3 Ag. You can see that the electrons cancel out there. So that would be the balance equation. Last thing I need to do is just to write the shorthand notation for this. So first I have that vertical line that separates out the anode from the cathode. That's the salt bridge. And then on the anode side, the reaction is the oxidation of chromium solid into chromium 3 plus. However, chromium solid also acts as the anode in this case. So then I would separate that out with a vertical line. So it's just chromium solid and then chromium 3 plus. And then on the right side, the silver ion becomes silver solid, but silver solid is also my cathode. So I'm going to write it that way. And then I have Ag plus right here. So that would answer the question that's being asked with everything that it's asking, which is the drawing of the diagram, the reaction, and the shorthand or the line notation.